Chapter 2, we're going to get into our discussion of derivatives. And derivatives have everything to do with slope. So, if we find the slope of a secant, as we learned in Chapter 1, that's the average rate of change. If we find the slope of a tangent, that's an instantaneous rate of change. So if we look at this thing here, if we want to find the instantaneous rate of change at this point right here, well, that would be the slope of the tangent there. And this isn't anywhere close. This is the slope of a secant. Now, if we move this thing around, come on, come with me. If we move this thing around where the point, oh boy, I'm moving too much here. Where we get 2 points that are pretty darn close to each other. Now this is starting to look more like a tangent. If we're talking about the point AF of A, XF of X, and XF of X is right here. If those points are really close, that secant line looks a whole lot like a tangent line. And to find the slope of that secant, which is pretty darn close to the slope of the tangent, we'd take f of x minus f of a, change in y, over the change in x. So, the instantaneous rate of change is going to happen as long as x and a are really close, kind of like we showed back here. If these points are really close, then we're going to have a secant. It's pretty darn close to a tangent. So let's find the equation of the tangent line, y equals x squared at the point 1, 1. And I know last year when you guys were in AB, talked a lot about the point slope form, and we'll use point slope form. Point slope form is y minus something equals our slope times x minus something. And that was a nice convenient way to write the equations of lines. And all we need is a point. Well, the x value is 1. I'll put a 1 in with the x. The y value is 1, so I'll put a 1 by the y. So y minus 1 equals the slope times x minus 1. Now we got to find the slope. Well, let's use this to find the slope. Now, we're talking about the point 1, 1, so we're going to take the limit as x approaches 1 of f of x. Well, that's right here. Minus f of a. Well, in this case, a is 1, remember. What is the value of the function at 1? Well, at 1, the value of the function is 1 over x minus a, x minus 1. Now, this is a limit that if we substitute the 1 in place of the x, we're getting 0 over 0. So what tool are we pulling out of the toolbox? Well, probably the factor tool. We're going to take the limit as x approaches 1, x plus 1, x minus 1 over x minus 1. And the x minus 1's cancel out. Now they don't cancel out. They factor out to be a 1. They're identical. So when we put a 1 in here, we get 2. And that's the equation of the tangent line. So this is how we can find slope. And that was really helpful that we knew that we were approaching 1. When we know what A is, when we know what we're approaching, this is a great form to find the slope. When we don't know what we are approaching, then this form right here will help us find the slope at any value of A. So let's practice how to use that. If we don't know what A is, then this form of a slope at a particular value, particular but unknown value of A, is going to help us find the slope at any value of A. And keep in mind, velocity is the slope of the tangent of any position time graph. All right. So we got this same example we had back in chapter 1. Find an expression for the velocity at any time. Well, all right, so we're going to use this limit as h approaches 0 form. F of A plus h minus f of A divided by h. We don't know what A is. So what I've got to do, this is P of t, and this is what I am doing to t to find the position at any time. Well, what if I put an A plus h into the function in place of the t? I'm going to find a limit as h approaches 0. And I'm going to have 450 minus 4.9 A plus h squared minus f of A. This function right here, but replace the variable with an A. So that's going to be 450 minus 4.9 A squared, all divided by h. Well, that's a pain, and the next step's even a greater pain. Because now I got to expand this thing. I'm going to take the limit as h approaches 0. And I'm going to have 450 minus. Now, if I were to square that and square that correctly, and then multiply by 4.9, well, let's see. I would have a squared, but I got to multiply by 4.9. So I'm going to have 4.9 a squared. When I square this, the middle term would be 2ah times 4.9 would be 4.9, up 9.8 ah. If I square this correctly, it would end with an h squared, but when I multiply that by 4.9, I would have 4.9 h squared. Now I got to subtract this 450 minus 4.9 a squared. And I'm supposed to divide that all by h. Well, that's a pain, but now I think we see that there are some things that are just going to plain and simply go away. First of all, 450 minus 450. I've got negative 4.9 h squared. Oh, I'm sorry. Negative 4.9 a squared minus negative or plus 4.9 a squared. Those two, when combined, result in 0. Now, every single time I do this, I will find that this guy over here, this f of a, is going to completely go away. If it doesn't, I've probably messed up. So let's take what remains, and let's take what remains and divide it all by this h. We will have the limit as h approaches 0. And this thing divided by h, remember, we are subtracting. So we're going to have negative 9.8 a. We will be subtracting 4.9 h squared divided by h. So we'll be subtracting 4.9 h. And if h is approaching 0, I guess all we end up with is negative 9.8 times a. And a is some value of time. And so, an expression for the velocity at any time. The velocity at some value of a is equal to negative 9.8 a. So find the velocity at 5 seconds. Well, the velocity at 5 is negative 9.8 times 5, which is negative 49. And I think that the units that we had was meters and seconds. And when we did this back in chapter 1 and we estimated what we thought the velocity would be, that instantaneous rate of change at 5, I think we came up with negative 49. If I want to find the velocity at a time of 7, velocity at a time of 7, negative 9.8 times 7. Oh, let's see. 6 carry the 5. 63, 68. Negative 68.6 meters per second. And if I mess that up, fix it. Find the velocity when it hits the ground. Well, no problem. All you got to do is find out when it hits the ground, multiply that by negative 9.8, and you got it. Find out when it hits the ground is kind of an adventure, however. I do know, let's see, I got to go back here. Position at any time. 450 minus 4.9 t squared. $450 minus 4.9 t squared. And I'm interested in when the position is at 0. When is this thing on the ground? The ground is a position of 0. So I think I'm going to say 450 equals, if I add 4.9 t squared to each side. And now I got to grab my calculator and figure out what I get for t. Why don't you figure out what you get for t? Now, if they asked me, when does this thing hit the ground, I would have said 4.583. I got to be accurate to 3 decimal places. They want the velocity when the object hits the ground. I'm not rounding this thing off. My answer's got to be accurate to 3 decimal places, so I'm using all of these decimal places till I get to my final answer, which is the velocity. And the velocity at this 9.583 yada, 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 yada. I'm using all of those numbers on my calculator, and I am multiplying them by negative 9.8. And I think we get negative. Now there's an 8 here. So I can truncate this and just say negative 93.914 or negative 93. 0.915 if I round. Either one of those is acceptable to the College Board. And that concludes our discussion, our initial discussion on derivatives.